Okay, my last video cut off unexpectedly, and I apologize for that, but we were just getting into this idea of if the electron is not experiencing the full force of the nucleus, what's the partial force that it is experiencing, and that is called effective nuclear charge, and it gets the abbreviation of Z, okay, because Z is actually stands for charge, and then it gets a little EFF for effective, so most chemists refer to this as ZEF, is how they the slang name for it per se. Okay, so we're going to talk about how you calculate ZEF and what it means, and then that'll be the end of this video on effective nuclear charge. Okay, so there's a formula for ZEF, and it says this. Okay, and it doesn't really mean much to us, but the formula is ZEF equals Z minus S, where Z is the number of protons, and S is the number of core electrons. So this is really a very simple formula. So let's talk about sodium. Okay, if we think about sodium, we can even do a configuration if you want. It's not necessary, but 1s2, 2s2, 2p6, 3s1. Okay, so if we're going to calculate a ZEF for sodium, the way ZEF works is we take the protons in sodium, which would be 11, and we subtract from it the number of core electrons. So remember, what's not core is valence, and what's not valence is core. So sodium has 1 valence electron and then 10 core. So the ZEF on a sodium atom is 1, or plus 1, which conveniently is its charge. It's kind of interesting how that works out. So what this means is that, so if you think about it, if we were to draw the atom here, you have 11 protons in the nucleus, you have 10 electrons in the inner energy levels, sorry if I just misspoke, and you have that 1 valence electron out here as your valence, okay? So if this is sodium, the question was, what kind of attractive force is this electron feeling from the nucleus? Well, before we started this discussion, you might be inclined to say it's experiencing a positive pull, per se, of 11. But it's not, because these 10 core electrons are in the way. That's that idea of shielding. So we do this little formula to think about what it really then is that electron feeling. It's not feeling a pull of 11. It's really only feeling a pull of 1, okay? Because these 10 core electrons get in the way. So that is ZEF. So if we do another one, and let's say same period, let's talk about chlorine. So chlorine is 1s2, 2s2, 2p6, 3s2, 3p5, okay? So again, ZEF is protons minus core, so chlorine has 17 protons, and the same number of core, right? Think about it, because they're both in the third energy level. So here are your cores for chlorine, and then here are your valence. Remember, what's not valence is core. Excuse me. So if chlorine has 7 valence, it has 10 core. So 17 minus 10 gives me a ZEF of positive 7 in this case. So if I were to think about this discussion, here's chlorine, 17 protons in the nucleus, 10 core electrons, right, and 7 valence, I thought I messed up. 7 valence electrons. The question here is, what charge is, or what attractive force are these valence electrons feeling? And again, you might have been inclined to say a charge or a pull of 17, which is the nucleus, but that's not true, because these electrons get in the way and they shield. And so in this case, chlorine is experiencing the valence electrons in chlorine are experiencing a attractive force of positive 7. So, what a question could be is, which kind of atom experiences a higher ZEF? And in this case, that's your chlorine.